Hi everyone. Stack Lessons here. We've got 20 more questions in the books today. Topic is AI search endpoint sizing, provisioned throughput, and RAG retrieval architecture. Each gets a 10-second countdown so you can commit to an answer before the reveal. Take your time. Time for another one. Question 1. Keep the constraints in view. A generative AI engineer at Meridian Insights is improving answer quality in a legal document RAG system. Documents are indexed as 512 token chunks, which provides strong retrieval precision. However, the LLM frequently produces incomplete answers because a single 512 token chunk rarely contains enough surrounding legal context for accurate reasoning. Uniformly enlarging chunks to 2048 tokens degrades retrieval precision. Which retrieval strategy resolves this tension? Select one. Review the answer choices on screen. The correct answer is option A. Small chunks find it. Parent chunks give the LLM context. Parent-child retrieval is specifically designed for scenarios where the optimal chunk size for retrieval differs from the optimal context size for generation. Small 512 token child chunks are indexed and searched, preserving the precision that comes from tighter semantic boundaries. When a child chunk is retrieved, the system returns its larger 2048 token parent segment to the LLM, providing the surrounding legal context needed for accurate answers. This decouples retrieval granularity from generation context size without sacrificing either. Switching to semantic chunking produces semantically coherent sections, but does not guarantee that each section will contain sufficient legal context. Output size is variable and still unpredictable. Increasing the embedding model's context length changes what the model can encode during indexing, but does not alter the size of the text passages that are actually passed to the LLM at generation time. Reducing chunk size to 256 tokens would increase recall but decrease the already insufficient context per chunk, making the generation problem worse rather than better. Time for another one. Question 2. Separate fact from assumption. A generative AI engineer at Montclair AI has enabled inference tables on a model serving endpoint to capture all requests and responses for production monitoring. After several weeks of successful logging, a data engineer modifies the schema of the inference table by adding a new internal tracking column. Shortly afterward, the engineer notices that new requests are no longer appearing in the table. What is the most likely cause? Select one. Review the answer choices on screen. The correct answer is option C. Restarting the endpoint is the obvious fix, and wrong. Inference tables are tightly coupled to the schema and name of the delta table they were configured to write to at setup time. Modifying the schema of an inference table, including adding, removing, or renaming columns, breaks the logging pipeline and causes the endpoint to stop recording new requests and responses. Recovery requires provisioning a new table and reconfiguring the endpoint to target it. Restarting the endpoint does not resolve a schema mismatch. Logging stops because the underlying table contract has changed, and a restart alone neither restores the original schema nor re-establishes the logging connection. The 128 concurrent request default limit applies to simultaneously active requests and does not suppress logging for requests that complete successfully. The sampling fraction is a fixed value set during inference table configuration and does not reset automatically in response to schema modifications or any other table-level changes. Time for another one. We're on question 3. A streaming platform's trust and safety team is building an automated content policy enforcement system. The system ingests both thumbnail images and short video clips from creator submissions and must classify each submission for policy violations in a single model call, without a separate pre-processing pipeline. A generative AI engineer must select a foundation model API model that natively handles all required input modalities. Which model should they choose? Select one. Review the answer choices on screen. The correct answer is option A. One model natively handles video. Eliminate the others fast. Gemini 2.5 Flash is the correct choice because Gemini family models available through the Foundation Model API natively support all 4 input modalities: text, image, video, and audio. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4.6 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. Ready? Careful on question 4. This one has a trap. A generative AI engineer at Nexus Commerce is building a global product recommendation system. The vector store will contain approximately 2 billion product embeddings, and the team prioritizes fast nightly re-indexing of newly added products over achieving the lowest possible query latency. Which AI search endpoint type should they select? Select 1. Review the answer choices on screen. The correct answer is option B. 2 billion vectors rules out the standard endpoint immediately. Storage-optimized endpoints are designed for vector stores exceeding 1 billion entries and deliver 1020x faster indexing speeds, which directly addresses the team's priority of rapid nightly re-indexing at 2 billion embeddings. Standard endpoints are capped at approximately 320 million vectors at 768 dimensions and cannot accommodate a 2 billion vector corpus at all, making them an incorrect choice regardless of latency characteristics. Both endpoint types use the HNSW algorithm. HNSW is not exclusive to any tier and does not inherently support billion-scale corpora without storage-optimized infrastructure. Storage-optimized endpoints do not eliminate query latency. They introduce an approximately 250 millisecond latency increase compared to standard endpoints as a necessary trade-off for greater capacity and faster indexing. This one trips people up. 2 billion vectors is a lot. Let's look at the spec card. Imagine your team adds 50 million new products every night and needs them searchable by morning. With 2 billion total embeddings, your first question isn't latency, it's can this thing even hold that many vectors? Standard endpoints top out at about 320 million. That alone rules them out. Storage-optimized endpoints hold over 1 billion vectors. They re-index 10 to 20 times faster. Your nightly job finishes before your team wakes up. Yes, queries run about 250 milliseconds slower. That's the trade-off, and both endpoint types use HNSW, the same search algorithm, so that detail is a red herring. The question rewards re-index speed, not query latency. Let us switch gears. Let's look at question 5. A generative AI engineer is preparing a Foundation Model API endpoint for a customer support assistant ahead of production launch. Load testing revealed that token generation rates fluctuate significantly under variable traffic, causing inconsistent response times. The team needs a guaranteed minimum performance floor while still allowing the endpoint to scale up automatically during demand spikes. Which configuration achieves this? Select 1. Review the answer choices on screen. The correct answer is option D. The parameter names are self-documenting. Read them literally. Specifying min_provisioned_throughput and max_provisioned_throughput is the correct configuration for provisioned throughput endpoints, because these two parameters define the guaranteed performance floor and the upper scaling ceiling, enabling the endpoint to auto-scale within that range based on actual traffic. This ensures the minimum performance is always reserved while absorbing spikes up to the configured maximum. Setting temperature and max_tokens influences the content and length of model outputs, but has no effect on the infrastructure's throughput capacity or response consistency under load. Batch size and request timeout are infrastructure tuning parameters, but are not the provisioned throughput scaling mechanism for foundation model APIs. Switching to pay-per-token is explicitly recommended for early-stage, low-volume applications and not for high-throughput production workloads. It does not provide a guaranteed throughput floor. 3 concrete patterns so far. Parent-child decouples retrieval granularity from generation context size. Schema changes silently break inference table logging. Storage optimized is mandatory above 1 billion vectors. Let us switch gears. Let's look at question 6. A generative AI engineer has developed 2 RAID configurations for a contract review assistant at a law firm. They want to determine which configuration produces superior generated summaries. Human reviewers will evaluate outputs from both configurations against the same queries. Which evaluation approach captures preference differences most directly? Select one. Review the answer choices on screen. The correct answer is option C. Pairwise means head-to-head, one output always wins. Pairwise comparison evaluation presents both outputs side by side to human reviewers or an LLM judge, and asks which is superior for each query. This approach captures relative preference more sensitively than absolute scoring, and is specifically designed to compare 2 competing systems by showing the judge the full contrast between them on the same input. Single output scoring assigns each response an independent score on a fixed scale. While useful for monitoring absolute quality, it is less sensitive to subtle differences between 2 similar configurations because scores can converge without revealing which is consistently preferred. Recall that K measures retrieval coverage, not the quality of generated summaries that result from retrieval, so it evaluates the wrong component of the pipeline for this comparison. G-Evil uses chain-of-thought prompting to rate each output independently on a numeric scale, which again produces absolute scores rather than head-to-head preference judgments between the 2 configurations. Let us switch gears. Let's handle question 7. Quick check. A content moderation team at Meridian Streaming needs to analyze both short video clips and thumbnail images in a single API call to detect policy violations. The system must handle both modalities natively without pre-processing video into individual frames before sending to the model. Which foundation model API model should they select? Select one. Review the answer choices on screen. The correct answer is option D. Content moderation at scale demands native video, not frame extraction. Gemini 2.5 Flash natively supports all 4 input modalities: text, image, video, and audio, making it the only option capable of ingesting both video clips and thumbnail images in a single API call, without requiring frame extraction or other pre-processing. Claude's Sonnet 4 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively processing video content for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. Keep your focus here. Question 8. Convert the story into selection criteria. A generative AI engineer at Contesso Analytics is moving an LLM-based contract analysis service from prototyping to production. During prototyping, pay-per-token foundation model API endpoints were used. The production service is expected to handle a sustained, predictable volume of 8,000 requests per hour with strict latency SLAs. Which serving configuration change should the engineer make? Select one. Review the answer choices on screen. The correct answer is option B. 8,000 hourly requests means pay per token is over. Provisioned throughput is the recommended configuration for all production workloads. It allocates dedicated compute capacity and is specified by setting minimum and maximum provisioned throughput values, which guarantees consistent latency and throughput for sustained, predictable traffic. Pay per token endpoints share capacity with other workloads and are suitable for experimentation and early development where traffic is low and unpredictable, but they cannot reliably meet strict latency SLAs at high sustained request volumes. Adding auto-scaling rules to pay-per-token endpoints does not change the underlying shared capacity model and leaves the SLA exposure unchanged. Deploying multiple pay-per-token endpoints behind a load balancer multiplies the shared capacity problem without solving the latency guarantee concern. External models via AI Gateway add routing overhead and external dependency latency that actively work against a strict latency SLA. Keep your focus here. Let's check question 9. A genomics research institute is building a literature search system backed by Databricks AI Search. The corpus contains over 1.5 billion embedding vectors representing sentences from academic papers. The team has benchmarked their workload and can tolerate up to 300 milliseconds of additional query latency in exchange for being able to continuously index new papers at scale. Which endpoint type should the team configure? Select one. Review the answer choices on screen. The correct answer is option B. Above 1 billion vectors with latency tolerance accepted. Done. Storage-optimized endpoints are designed specifically for corpora exceeding 1 billion vectors. They provide 10 to 20 times faster indexing throughput compared to standard endpoints, which is essential when continuously adding new academic papers to a very large corpus. The documented trade-off is approximately 250 milliseconds of additional query latency, which this team explicitly accepts. Standard endpoints support approximately 320 million vectors at 768 dimensions, well below the 1.5 billion vectors in this corpus, making them insufficient regardless of configuration. Distributing across multiple standard endpoints adds substantial architectural complexity and does not resolve the capacity constraint inherent in each individual endpoint. Provisioned throughput is a configuration for model-serving LLM endpoints and has no relevance to AI search endpoint type selection. All right. Question 10. Wording first, memory second. A generative AI engineer at Osprey Analytics is working in an MLflow 3 workspace and wants to register a newly trained model to Unity Catalog using MLflow.register_model. Their workspace has a catalog named ML_prod, a schema named credit_risk, and they want the model called default_predictor. Which value should they pass as the model name argument? Select one. Review the answer choices on screen. The correct answer is option D. The separator is the whole question. One dot makes it right. Unity Catalog uses a 3-level delimited namespace for all managed objects including registered models. The required format is catalog.schema.model_name. So ml_prod.credit_risk.default_predictor is the correct argument to pass. Providing only the bare model name default_predictor without catalog and schema qualifiers either resolves to the legacy workspace level registry or fails outright when MLflow is configured with the Databricks UC registry URI, which is the default in MLflow 3. Forward slashes are not valid namespace separators in Unity catalog syntax and will cause the registration call to fail with an error. Colons are equally invalid as namespace delimiters for Unity catalog objects and will produce the same failure. Pairwise evaluation captures head-to-head preference that absolute scores miss. Unity catalog naming is a pure syntax test, 3-separated segments, no exceptions, no slashes. Okay. Question 11. Start with what the user needs. A generative AI engineer at a Datum is building a RAG application that must answer employee questions using both a large corpus of internal policy PDFs and live headcount data stored in a relational database updated daily. How should the engineer design the retrieval component to handle both data sources? Select one. Review the answer choices on screen. The correct answer is option D. Different data structures always demand different retrieval strategies. RAG applications use different retrieval mechanisms depending on data type. Unstructured content, such as policy PDFs, is best handled through vector similarity search. Documents are chunked, embedded, and indexed in AI search for approximate nearest neighbor retrieval. Structured relational data such as headcount records is best accessed through a SQL query interface that can filter rows exactly, aggregate counts, and join tables with precision that approximate vector search cannot match. Co-indexing all data in a single vector index produces poor results for structured data because numeric and categorical fields are not meaningfully represented by semantic embeddings. Converting database records to JSON documents and embedding them alongside the PDFs loses the ability to perform structured queries and introduces staleness, since the vector index does not remain in real-time sync with the relational database. Feature serving is designed to expose pre-computed feature values for low-latency inference at prediction time. It is not a retrieval layer for large unstructured document corpora. Here we go. Question 12. Eliminate before you select. A generative AI engineer at Tailspin Commerce is configuring Databricks AI search for a real-time product recommendation engine. The catalog contains 80 million product embeddings that are updated continuously as new items are added throughout the day. The application serves customer-facing recommendations and requires the lowest possible query latency. Which AI search endpoint type should they select? Select one. Review the answer choices on screen. The correct answer is option C. Every ROM option makes a confident and falsifiable claim. Standard endpoints store full precision vectors in memory, delivering query latencies of 20 to 50 milliseconds suited to real-time customer-facing requests, and they support both continuous and triggered sync modes, allowing the product catalog to reflect new items as they are added throughout the day without manual sync triggers. Storage-optimized endpoints separate storage from compute to serve billions of vectors cost-efficiently, but their query latency is approximately 250 milliseconds, far above the target for real-time recommendations. The claim that storage-optimized endpoints provide the lowest latency is incorrect. They are the higher latency option and are better suited to workloads where scale and cost matter more than sub-100 milliseconds response times. Continuous sync mode is not available on storage-optimized endpoints. Only triggered sync is supported, which means the catalog would only be updated when syncs are manually or schedule triggered, not continuously. Both standard and storage-optimized endpoint types support creating delta sync indexes. The architectural distinction lies in memory management, query latency, and sync mode availability. Let's slow down here. This endpoint choice trips up almost everyone taking the exam. Imagine you're running a product search for a live shopping app. Customers click and expect results instantly. Standard endpoint keeps all vectors in memory. At 80 million products, query latency runs about 20 to 50 milliseconds, fast enough to feel instant. Storage optimized separates storage from compute. It handles billions of vectors cheaply, but query latency jumps to around 250 milliseconds. Customers feel that. Then there's the sync trap. Continuous sync keeps your catalog fresh as new items arrive, but it only works on standard endpoints. Storage optimized supports triggered sync only. You manually kick it off. This question stacks two requirements: lowest latency and live catalog updates. Both point to standard. That's the punchline. Okay, let's get into question 13. A media company has completed development of a content moderation assistant using foundation model APIs on Databricks. During testing, the team used pay-per-token pricing. The application is now ready for production and will sustain approximately 10,000 requests per hour throughout the business day. What should the generative AI engineer recommend for the production deployment? Select 1. Review the answer choices on screen. The correct answer is option B. Any sustained production volume points straight to provisioned throughput. Provisioned throughput is the recommended approach for all production workloads, particularly those with sustained and predictable query volumes. It requires specifying min_provisioned_throughput and max_provisioned_throughput, and auto-scaling ensures consistent latency under load. Pay per token is explicitly designed for development, experimentation, and low-volume workloads, not high-throughput production scenarios where its economics and performance guarantees are less favorable. A self-managed GPU cluster introduces significant operational overhead for infrastructure management, scaling, and maintenance that foundation model APIs eliminate. Distributing pay-per-token requests across multiple endpoints does not address the fundamental cost and performance inefficiencies of pay-per-token at sustained production loads. Next up, question 14. One answer is too broad. A media streaming company is building a semantic search feature over 2.3 billion short video transcript segments, each embedded at 768 dimensions using a managed embedding model. The team started development with a standard AI search endpoint, but query performance is degrading as the index approaches its capacity ceiling. The engineer plans to migrate to an endpoint type suited for production scale. Which endpoint type should they select, and what operational trade-off should they expect? Select 1. Review the answer choices on screen. The correct answer is option A. Option D reverses the latency direction. That inversion is the trap. Storage-optimized AI search endpoints are designed for corpora exceeding 1 billion vectors, making them the correct choice for a 2.3 billion segment index. The known trade-off is approximately 250 milliseconds of additional per-query latency compared to a standard endpoint, offset by 1020x faster index synchronization speed. Running two parallel standard endpoints with application layer load balancing does not expand the per-endpoint vector capacity ceiling and adds unnecessary routing complexity. Increasing the embedding dimension changes the vector representation quality, but has no effect on an endpoint's maximum vector capacity, which is determined by endpoint type. The fourth option incorrectly describes the latency effect. Storage-optimized endpoints increase per-query latency by roughly 250 milliseconds rather than reducing it. Next up, question 15. Pick the complete answer. A generative AI engineer at Kestrel Systems is deploying a company-wide LLM platform on Databricks. Multiple departments will share the same foundation model API endpoint. The platform team has two requirements. No single department should be able to exceed its allocated monthly token budget, and any messages containing social security numbers or email addresses must have those values automatically masked before reaching the underlying model. Which two AI gateway features should the engineer configure? Select 2. Review the answer choices on screen. The correct answers are option B and option D. Each distractor solves a real problem, just not these two requirements. Rate limiting in AI Gateway allows the platform team to enforce token per minute or query per minute quotas at the endpoint, user, or group level, directly preventing any single department from consuming beyond its allocated budget and stopping cost overruns before they occur. PII detection and redaction automatically identifies personal information including social security numbers and email addresses within request content, and replaces those values with placeholder text before the request reaches the underlying model, satisfying the masking requirement at the gateway layer. Safety filters address harmful content categories such as hate speech and violence and are not designed to detect or redact personal identifiers. Traffic splitting distributes load across model versions or endpoints for routing purposes and does not enforce usage limits or mask sensitive content. Inference tables log requests and responses after the fact. PII would already have been transmitted to the model before the logged data could be reviewed. Let's slow down here. The AI Gateway features question is sneakier than it looks. Imagine you're the platform engineer at Kestrel Systems. 5 departments share one model endpoint. You have 2 jobs: stop any team from blowing its monthly token budget, and make sure no social security numbers ever reach the model. Safety filters sound tempting. They scan content, but they flag violent or offensive language, not personal identifiers. Inference tables seem like a compliance win, but they log after the model already processed the request. The SSN is already gone. Traffic splitting routes load across models, great for reliability, useless for budgets. Rate limiting is your budget cop. It cuts off a department the moment it hits its quota. PII redaction strips SSNs and emails before the request even leaves the gateway. Match the requirement to the tool, that's the whole trick. AI Gateway multi-select locked in 2 rules: rate limiting caps budget per group, PII redaction masks before the model sees data. Standard endpoints keep continuous sync. Storage optimized endpoints lose it. Now, question 16. The setup controls the answer. A generative AI engineer is building a RAG application for a legal research platform at Crestwood Legal. During evaluation, they find that small text chunks of around 200 tokens retrieve the most precise and relevant passages when matching user queries, but the LLM frequently produces incomplete answers because those small passages lack surrounding legal context. The engineer needs a strategy that preserves retrieval precision while giving the LLM enough contextual information to generate accurate, complete responses. Which chunking approach should they implement? Select one. Review the answer choices on screen. The correct answer is option A. Precision at retrieval, full context at generation, that's parent-child. Parent-child retrieval directly resolves the precision versus context trade-off. Small chunks around 512 tokens are used at retrieval time, so semantic matching is precise and focused, but when a chunk is selected, the system returns its larger parent segment of around 2048 tokens to the LLM. This gives the language model the surrounding legal context it needs without sacrificing the retrieval accuracy that larger chunks would compromise. Switching to large 2048 token chunks improves context, but degrades retrieval precision because a large chunk contains multiple concepts and produces a noisier embedding that matches queries less accurately. Semantic chunking determines boundaries by topic similarity and is a strategy for splitting text during ingestion. It is not a mechanism for expanding the context window provided to the LLM at generation time. A query classifier routes queries to different chunk sizes based on intent, but still returns only the matched chunk to the LLM, so the fundamental tension between precise retrieval and rich context remains unresolved. Let us keep moving. Question 17. Watch the exact wording. A generative AI engineer at Glenfield Media is using MLflow's built-in LLM as judge metric to evaluate the relevance of retrieved chunks to user queries. After running evaluation on a sample of 200 queries, the average relevance score is 1.8. A colleague argues this indicates critical failure and recommends rebuilding the index from scratch. How should the engineer correctly interpret this score? Select 1. Review the answer choices on screen. The correct answer is option D. The score only means something once you know the scale ceiling. MLflow's built-in LLM as judge relevance metric uses a fixed 4-point scale. 0 means not relevant, 1 means partially relevant, 2 means relevant, and 3 means highly relevant. An average of 1.8 falls between partially relevant and relevant, meaning most retrieved chunks have meaningful overlap with their queries, but are not consistently the ideal match. This indicates moderate quality with clear room for improvement through iterative tuning of chunk size, overlap, or retrieval parameters, not a catastrophic failure requiring a full index rebuild. There is no platform-defined threshold at 2.5 that triggers mandatory remediation. The scale is bounded at 0 to 3, not 10 points, so the score is directly interpretable without normalization against an external reference. Let's stop on this one. Misreading the scale is exactly the trap this question is testing. Imagine your quiz came back graded 1.8. But nobody told you if it's out of 3 or out of 10. That one missing fact changes everything. The built-in relevance judge in MLflow runs on a 4-point scale. 0 means not relevant, 1 means partially relevant. A score of 1.8 lands right here, between partially and fully relevant. 2 means relevant, 3 means highly relevant. That puts 1.8 in moderate territory, not disaster. The colleague's panic assumes a 10-point scale that doesn't exist, and that 2.5 threshold? Completely made up. Tune chunk size and retrieval parameters first. A full index rebuild is nowhere near warranted. Now, question 18. Coming up, a generative AI engineer at Litware has deployed a RAG-based customer escalation assistant using a provisioned Throughput endpoint. The infrastructure team wants to monitor whether the endpoint is approaching its allocated capacity ceiling, so they can decide whether to increase provisioned throughput. Which metric should the engineer track? Select 1. Review the answer choices on screen. The correct answer is option C. Tokens per second directly measures provisioned capacity consumption. For a provisioned throughput endpoint, tokens per second is the primary operational metric. This value directly reflects how much of the provisioned capacity is being consumed relative to what was allocated, giving the infrastructure team a clear signal for scaling decisions. When tokens per second approaches the configured maximum, additional provisioned throughput should be allocated. When it is consistently far below the minimum, capacity may be over-provisioned. Model perplexity is a training time measure of how well a model predicts held-out text, and has no relevance once the model is deployed in production. The number of active delta sync index synchronization tasks is an indexing infrastructure metric for AI search, and is unrelated to the serving endpoint's language model capacity. Average vector similarity score from AI search describes retrieval quality, how well retrieved documents match user queries, not the capacity utilization of the language model endpoint. Time for another one. Question 19. Several choices sound plausible. A generative AI engineer at Fairview Commerce is building a customer service assistant that must answer questions about product specifications stored in unstructured PDF manuals and current inventory levels stored in a relational database table refreshed hourly. Which two retrieval approaches should be combined in this assistant? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Embedding stock counts into a vector index sounds unified but fails. Unstructured document sources such as PDF manuals are best served by chunking, embedding, and indexing them in a vector store, so the assistant can find relevant product specification sections through semantic similarity search. Structured relational data such as inventory levels requires SQL queries against the source database to retrieve accurate and current values. Embedding database rows into a vector index produces poor semantic representations of numeric stock counts and introduces staleness risk for data that changes every hour. Consolidating both data types into a single vector index conflates retrieval patterns that are fundamentally different and degrades accuracy for structured queries. Feature serving is designed for low-latency retrieval of pre-materialized feature values and is not a mechanism for indexing document embeddings. Time for another one. Question 20. Do not answer a different question. A generative AI engineer at Tailspin Research is configuring hybrid search on their AI search index. Dense vector search captures semantic similarity but misses exact keyword matches. BM25 keyword search finds precise terminology but cannot bridge conceptual synonyms. The engineer needs to merge ranked result lists from both approaches into a single unified ranking. Which algorithm does Databricks AI Search use for this combination? Select one. Review the answer choices on screen. The correct answer is option B. The algorithm name and its default parameter are both on the exam. Databricks AI Search uses reciprocal rank fusion with a default RRF_param value of 60 to combine ranked result lists from dense vector search and BM25 keyword search into a single hybrid ranking. RRF computes a combined score based on each document's rank position in each individual result list, promoting documents that appear highly in both lists without requiring scores to be on the same scale. Cross-encoder re-ranking applies a neural model to rescore candidate pairs and can complement but does not replace the initial ranking combination step. Maximal marginal relevance addresses diversity within a single result set rather than merging two independently generated ranked lists. Linear score interpolation requires vector similarity and BM25 scores to be normalized to the same range before combination, which is not how Databricks implements hybrid search. This question hides 4 real algorithms. Let's decode which words point you to the right one. Imagine 2 sorted piles of results, one from vector search, one from BM25. Your job is to combine them. The question says merge ranked result lists, not combine scores. That kills option D. Linear interpolation needs raw normalized scores, not rank positions. Then spot Databricks AI Search, that's a vendor fact. All 4 options are real algorithms. Databricks ships exactly one. Reciprocal rank fusion, RRF, with RRF_param of 60. Single unified ranking means the initial merge step, not a neural rescore pass, so cross-encoder is out. And maximal marginal relevance, MMR, addresses diversity inside one list, not merging two. The question rewards the vendor default, not the theory. 3 takeaways from this session. First, storage-optimized endpoints support over 1 billion vectors with 1020x faster indexing, but add 250 milliseconds of query latency. Second, parent-child indexes small chunks for precision but returns large parent segments for LLM generation context. Third, provisioned throughput with min and max parameters is always the correct serving choice for sustained, predictable production workloads. Specificity is what wins here, not just storage optimized for big indexes, but 1 billion vectors, 250 milliseconds, triggered sync only, RRF at 60, and the 0 to 3 judge scale. Lock those exact numbers in.